Alright, I've got a couple of spring questions here. We've got a normal spring here. We put a kg on it and it stretches to this far if you gently lower it. And then we'll look at this other bit here, but for now we've just got this, it stretches this far. It has a length of 70 centimeters. So what's the spring constant? The two formulas for springs are the spring potential energy is a half k change in x squared, and force equals k change in x. This is Hooke's law. We don't know anything about the energy yet. Well, in fact, I wouldn't use the energy. What we're going to use is just the simple stretching one for this first question to find out the spring constant. So if we rearrange that, we divide both sides by change in x, we get F over change in x equals k. And put the numbers in. It's 1 kg that's been added, so that's 10 newtons. And it's been stretched from 40 to 70, that's 30 centimeters, which equals 0.3 meters. And that's 33.3 newtons per meter. Okay, the big mistake here was this conversion that students made. Alright, next question. So on the next page of the exam there was these graphs here, and so there are all the graphs. Oops. Well, let's just read what it says. It says the spring's pulled down another further 10 centimeters from 70 to 80 and it's released so it oscillates. So that's looking at this diagram here, and it was here, it's pulled down to 10, it oscillates up and down and up and down and up and down between these two things here. So that's the situation we've got going on. And they've got all these graphs we can choose from, and the questions I've got over here. So which of the graphs shows the variation of kinetic energy of the system plotted against the length of the stretched spring? So let's draw the spring over here in green. So as it's all the way down, and then bounces up to the top, and bounces all the way down again. As it's at the bottom, it bounces up and down and up and down. Its velocity, as it gets to the bottom and turns around, its velocity is 0. As it gets to the top, it turns around and come back down, its velocity is 0 at the top as well, and then 0 at the bottom. As it goes through the middle, its velocity is highest. Velocity is large, and then as it comes down again to here, its velocity is also large, a big number. So the graph we're looking for is when it's at 60 centimeters, which is the top here, its velocity is 0. When it's at 80 centimeters, no, sorry, my mistake, its velocity is 0. We know kinetic energy equals half mv squared. So whenever velocity is 0, kinetic energy is also 0. At there, and at the top as well, kinetic energy equals 0. So this is a graph of kinetic energy. At the bottom at 80 centimeter stretch, it's 0. At the top at at the top here, which is 60, and this is down the bottom, which is 80. It's both 0, and then it gets bigger as it goes through the middle and back down to 0. So which graph has something that looks like that? I'd say D is the answer to that one. Alright, which variation shows which best shows the variation of the total energy of the system? So as it bounces up and down, we've got spring potential energy, and we've got gravitational potential energy, and we've got kinetic energy. And it changes between those three, but the total energy in this case stays the same all the time. So we're looking for a graph that has a total energy just flat, and that's the answer C. Which of the graphs shows the variation of the gravitational potential energy of the system measured from the lowest point being 0 energy against the length of the stretched spring? Alright, so when it's down the bottom here at 80 centimeters, and then it goes up to the top, bounces up to the top here, which is 60 centimeters, He's already said at the lowest point down here, the gravitational potential is 0. As it gets higher, the gravitational potential increases. So we're looking for a graph that at, here's 60, here's 80. 80 is the lowest. It goes through 0 and it's high up here. Which graph looks like that? So far B does. Is there any others? No, just B. Cool, so the answer to that one is B. And the last one, which of the graphs shows the variation in spring potential energy plotted against the length of the stretched spring? Give reasons for your answer. So we've got to do working and the answer. Right, so it turns out, this is an important part of our answer, I'm going to write it here, the spring potential energy equals 0 when no mass is attached. E.g. At 40 centimeters. Just going back to this diagram here. The spring potential energy is 0 here. Now remember the gravitational potential energy question, just the one previous. They've said that down here, gravitational potential 0. They said that at the bottom, and then obviously increased there. Now as this stretches out, it gets more and more spring potential energy down the bottom. And a mistake some students made was said that this point here is the 0 point. But no, the 0 point for spring potential energy is always where it has no mass. Always where it has no mass. So no mass here, spring potential energy is 0 here. So it's increased at this point, and it's increased again at 80. So here, spring potential energy equals 0. When it's down to 60 centimeters, spring potential energy is a little bigger, just a little arrow, just show it's got bigger, and when it's down to 80, spring potential energy this is 80 centimeters, is bigger again. The other thing, so we want 0 at 60, we want a graph that looks like, we want a graph that looks like, if it was going to 40, there'd be 0 up here, oh, my mistake, 0 at 40 centimeters, at 60 and at 80. At 60 it's a bit bigger, and at 80 it's a bit bigger again. So that's the graph we want to look for. So if we look for our graphs now, looks like it's 0 at 40. Well, that's 0 at 60, so it's not the case. We've got these three to choose from. Okay, well this one could go down to 0 at 40. This one possibly could go down to 0 at 40 as well. This one possibly could go down to 0 at 40. It doesn't look like it would have to change. But it could be really any of three of these. Because at least it doesn't start at 0 at 60. It turns out the answer is F, and I'm going to show you why now. Because spring potential energy equals a half K change in X squared, this means that plotting spring potential energy versus change in X gives a quadratic shape. Because you've got SPE equals change in X squared. That square gives it the quadratic shape, and a quadratic shape looks like that. And that is why it's definitely F. The quadratic shape is there, you can see it, and it also, if you extend this, you see this line will go down to 0 at 40, which is what we got in the first point. So it must be graph F. This was certainly a hard question. I had a similar question in 2013. The hardest question was about that, knowing that the spring potential energy is 0 when there's no mass on it.